Chapter 4 of the workshop is where you'll get familiar with interrupts and the timers. You'll use the timer to generate interrupts to the main routine. If you're not already familiar with the concept of microcontroller interrupts and interrupt service routines, now would be a good time to look up that topic online.
The LM4F Nested Vectored Interrupt Controller, or NVIC, is tightly coupled to the central processing unit. It handles all of the exceptions and interrupts that come into the CPU. There are 8 programmable priority levels and priority grouping. In most interrupt vector tables, you'll see that the priority levels are already set by the manufacturer and you have no input into what they are. That's not the case on this device. You can go in and reprogram the priorities as you like. The device has 7 system level exceptions and 65 interrupts that it handles. It also has a state machine driven automatic state saving and restoration for the state of the processor, as well as automatic reading of the vector table entry to very quickly facilitate going into interrupt service routines and back out. One of the first rules that you learn when you're programming interrupts on a microcontroller is to not nest interrupts. And one of the first rules that you break is you nest the interrupts. You need to get to a very low latency motor control or a temperature sensor or some device. You need to get to it very quickly, and you have other interrupts that are too long. You have to do them on most microcontrollers in software. You have to go back in, re-enable the interrupts you want to preempt some other interrupt. You do that in software. Here, you can do that in the NVIC. You can make interrupts preemptive and you can nest them. You can also interrupts can also be tail chained, which is something I'll explain in the next few slides. Interrupts are deterministic. They're always 12 cycles before they actually hit the interrupt service routine, or 6 cycles if they're tail chained. So taking a look at the diagram at the bottom, we can see here's a main application with a couple of interrupts going off. If you take a look from the left to the right, the first thing that goes off is motor control interrupt service routines. Something like the PWM, the ADC, something that's handling motor control. Motor control has to be extremely low latency. You can't wait. You must take them. So here comes along a second interrupt. This is a motor control ISR. You can see the second one occurring. That's fine. Well, here we are in the third instance here. A communication interrupt service routine, like the CAN, has started operation. We can't wait for the communications ISR to complete. So the motor control ISR preempts that. The interrupt interrupts, the motor control interrupts the communications ISR and runs right in the middle of it. At the end of that ISR, it transfers its control back to the original communication ISR. Remember, motor control ISRs cannot wait. They must be low latency. Communication ISRs, on the other hand, tend to have buffers associated with them, and they can generally wait. In the fourth instance, another motor control ISR goes off. In the fifth instance here, a communications ISR goes off. In the next one, a motor control interrupt service routine went off, and then sometime in the middle of that, a communication ISR went off. You can see that the transfer of control went directly from interrupt service routine to interrupt service routine. That's called tail chaining, and we're going to see more of that in just a moment. The first thing to look at in terms of improved interrupt latency is tail chaining. Here in this situation, we have 2 interrupts that basically go off at the same time. IRQ1, which is the highest priority, and IRQ2. In a typical processor, the interrupts would go off. It would push the state of the processor, run the highest priority interrupt service routine, pop the state of the processor, see that there was another interrupt pending, push the state of the processor, run the second service routine, and then pop the state of the processor again. Well, the pop and the push right there in the middle are doing the exact same thing in opposite directions. So there's no need to do those. The Cortex M4 interrupt handling is all in hardware. So we have a very short push at the beginning, and then we see that we run interrupt service routine 1. When the interrupt service routine is completed, the NVIC detects that there is another interrupt pending and does a 6-cycle tail chaining to then go to send the execution to the next interrupt service routine without having to come all the way back up to main. So you can see a significant savings in terms of in between interrupt service routine interrupt latency. The next item in terms of NVIC interrupt latency is called preemption. Well, this isn't preemption in the typical thought. This is preemption of the pop or push process. So you can see the diagram at the top shows the interrupt request for the highest priority interrupt going off. We service it, it's done, and then we have a second interrupt go off. Take a look there where the typical processor is doing its thing. Interrupt service routine 1 is run. At the end of that, we do a pop, and then during the pop is where another interrupt goes off. Well, in a typical processor, it's unable to do anything about that. It continues its pop process. It then pushes the state of the processor because it detected another interrupt happening. It ran interrupt service routine 2, and then it popped again. A lot of cycles being wasted. If we take a look at the Cortex M4, ISR1 runs. Anytime during the pop process, if we get another interrupt request come in, we can click, go right into a tail chain. We can move the stack pointer back, grab interrupt service routine 2, run interrupt service routine 2, and then pop, so that we can do as close to a tail chain as possible and waste the least amount of cycles. The next NVIC interrupt latency issue to look at is late arrival. In this case, we have the lower priority interrupt, IRQ2, going off before the higher priority. What we'd really like to do is we'd like the processor to transfer and handle interrupt request 1 before interrupt request 2, if that's possible. In a typical processor, it would be starting to push the status of the processor for IRQ2. As soon as it detected that there was a higher priority, it would finish the push, start a second push, and then go through an entire sequence where it did push ISR1, pop, push ISR2, and then pop. A significant amount of cycles wasted here. The Cortex 4, on the other hand, the NVIC will see during the push process that a second interrupt has happened. It will simply transfer the execution to ISR1 instead of ISR2 and run ISR1. At the end of the interrupt service routine, it will then tail chain into ISR2 and then pop at the end of that. A significant savings in terms of interrupt latency. In the Cortex M4 interrupt handling, it's totally automatic. There's no instruction overhead that on entry, the machinery automatically pushes registers R0 through R3, R2, the LR, the PSR, and the program counter onto the stack. In parallel, the interrupt service routine, the address for it, is prefetched onto the instruction bus. The ISR is then ready to start executing as soon as the last stack push is complete. Any further pushing of registers will be handled by the compiler. On the exit side, the processor state is automatically restored from the stack. In parallel, the interrupted instruction, the address of it, is prefetched, ready for execution upon completion of the stack pop. Again, any other registers that the compiler has decided to save will have to be done by the compiler. System level exception types on the Cortex M4 include reset, the non-maskable interrupt, hard fault, memory management fault, bus faults, usage faults, and you can see the rest down here. You can see the priority levels of -3, -2, and -1. Those are set. Those are programmed into the device and cannot be changed. A hard fault is something that might happen as a bus fault. For example, if you fail to turn on a peripheral when you try to access it, you'll get a bus fault. If you get a memory protection unit violation, that'll happen in vector number 4 as a memory managed fault. Now, all the rest of these, all the way down systic, pendsv, all the rest of these are programmable. You can come in and configure these as you like. So if you actually wanted one of your peripheral interrupts to be above a memory management fault, which is probably a mistake, you can do that. You can do that at configuration time. You can do that during runtime if you choose to. The Cortex M4 vector table is shown here. After reset, the vector table is located at address 0. Each entry in the vector table contains the address of the function, the handler, the ISR, to be executed. If you look down at the bottom at the initial SP value, that value at address 00 is used as the starting address of the main stack pointer. You can relocate the vector table if you need to. That's typically done by a bootloader. By writing to the V table register, you have to align this on a 1 KB boundary. If you want to, you can open up Startup under ccs.c for editing in your lab to see the vector table coding and how that's done. But you can see this going from bottom to top for the entire vector table. The General Purpose Timer Module, or GPTM, has 6 16 or 32-bit and 6 32 or 64-bit general purpose timers. Those can be split up into 12 16s, 32s, or 12 32 64s. They can be used for capture, compare, or PWM. The timer modes we have available, we have one shot, we have periodic. We can do an input edge count or a time capture. We can have a 16-bit prescaler on that if you want to count a number of counts before you actually count that number. PWM generation with a software inversion. We also can do real-time clock. The timers can count up or down. We have simple PWM here on the general purpose timer modules with no deadband generation. If you need deadband generation in your device, you need to get a device that has the PWM module, the motion control module, that has a full set with deadband generation as well. There's support here for timer synchronization so that reloading the timers happens simultaneously, for daisy chaining the different timers together, and for stalling during debugging. Now these timers can also trigger ADC samples, A to D conversions, or DMA transfers.
Lab 4 will use the general purpose timer to count down from a preset value. When the timer reaches 0, it will generate an interrupt and reload the timer. The interrupt hardware on the LM4F device will then find the correct address of the interrupt service routine you've written and execute it. These are all real-world skills that you'll need over and over again when working with any microcontroller. We've already created the Lab 4 project for you with an empty main.c, a startup file, and all the necessary project and build options set. You already paid your dues, you did that in the first 2 labs. Maximize CodeComposer Studio and click Project, Import Existing CCS Eclipse Project. Make the settings shown below and click Finish. Select your search directory in the Stellaris boards, My LaunchPad board folder, Lab 4 CCS. You should see Lab 4 come up as checked in the Discovered Projects folder. Make sure that the Copy Projects into Workspace checkbox is unchecked. It's in the My LaunchPad. Lab 4, CCS, OK. So it comes up checked. Again, make sure that the Copy Projects into Workspace checkbox is unchecked. And click Finish. In step 2, expand the lab by clicking the plus to the left of Lab 4 in the Project Explorer pane. Open main.c for editing by double-clicking on it. And you can type or you can copy-paste from the PDF the following 7 lines in the main.c. The hardware interrupts, those are the macros that define the interrupt assignment on Stellaris devices for the NVIC. The memmap, we saw those, we saw the types, the system control. Interrupt defines the macros for the NVIC controller. GPIO.h we saw before. Timer.h defines and has the macros for the timer API. In step 3, We're going to compute our timer delays using the variable period. It's a unsigned long, so if you're wondering if that's a U1 or that's a UL period, create main along with the unsigned long variable for this computation. Leave a line for spacing and type or paste the following after the previous lines. Next, we need to do the clock setup. In step 4, we're going to configure the system clock to run at 40 megahertz like we did in Lab 3 with the following call, the syscontrol clock set API. Leave a blank line for spacing and enter this line of code inside of main right after the unsigned long UL period. In step 5, like in the previous lab, we need to enable the GPIO peripheral and set the pins connected to the LEDs as outputs. Leave a line for spacing and add these lines after the last ones. That enables the port F GPIO peripheral, and it sets pins 1, 2, and 3 as outputs. In lab step 6, again, before calling any peripheral-specific driver lib function, we must enable the clock for that peripheral. If you fail to do this, it will result in a fault ISR. The second statement, you can see here we have a syscontrol peripheral enable for the timer 0, and then the second statement configures timer 0 as a 32-bit timer in periodic mode. Note that when timer 0 is configured as a 32-bit timer, it combines the two 16-bit timers 0A, timer 0A, and timer 0B. See the General Purpose Timer chapter of the device datasheet for more information on this. Timer 0 base is the start of the timer registers for timer 0. And you guessed it, the peripheral section of the memory map. Add a line for spacing and place the following 2 lines of code after the previous ones. In step 7, to toggle a GPIO at 10 Hz and a 50% duty cycle, you need to generate an interrupt at half of the desired period. So that would be at 5 Hz. So first, calculate the number of clock cycles required for a 10 Hz period by calling syscontrol clock get and dividing it by your desired frequency. Then divide that by 2, since we want a count that's half of that for an interrupt. So we can actually use this API to reach over and get the system clock. In case you might be changing the system clock in your code, you can go and get it dynamically. This calculated period is then loaded into the timer's interval load register using the timer load set function of the driver lib timer API. Note that you have to subtract 1 from the timer period since the timer interrupt fires at the 0 count. Add a line of spacing and add the following 2 lines of code after the previous ones. In step 8, next we have to enable the interrupt, not only in the timer module, but also in the NVIC, the nested vectored interrupt controller, the Cortex M4's interrupt controller. Int master enable is the master interrupt enable for all interrupts. Int enable enables the specific vector associated with the timer. Timer int enable enables a specific event within the timer to generate an interrupt. In this case, we're enabling an interrupt to be generated on the timeout of timer 0A. Add a line for spacing and put the following 3 lines of code after the previous ones. You can see there's the interrupt enable for timer A. We're saying generate an interrupt when there's a timeout, and then we're switching on the master enable switch for all interrupts on the part. So in lab step 9, finally we can enable the timer to start counting. This will start the timer and interrupts will begin triggering on the timeouts. Add a line for spacing and type the following line of code after the previous ones. So this enables the timer to go off and start running. In lab step 10, the main loop of code is simply an empty while loop, since the toggling of the GPIO will happen in the interrupt routine. Add a line for spacing, and then add the following lines of code after the previous ones. In step 11, since this application is interrupt driven, we must add an interrupt handler for the timer or interrupt service routine. In the interrupt handler, we must first clear the interrupt source and then toggle the GPIO pin based on the current state. Just in case your last program left any of the LEDs on, the first GPIO pin write turns off all 3 LEDs. Writing a 4 to pin 2 lights the blue LED. Add a line for spacing and add the following lines of code after the final closing brace of main. So you can see this is the timer 0 int handler, which has a int clear to clear the timer interrupt. We read the pin back, we write to it to turn it off, and then we turn on the blue LED, which is a 4. Take a look at your code at this point. If it looks wrong, remember how we corrected it in the previous lab to correct the indentation. Source, correct indentation. Very nice. In step 12, click the Save button to save your work. Take a look at the code that you see in the workbook. It should look something like that. Hopefully, something pretty close. So okay, we have the main code. We have the interrupt handler. We're missing one piece here. We're missing the vector that when the interrupt fires, that it's going to have us go over and actually run timer 0 int handler. So in step 13, open startup under ccs.c for editing. This file contains the vector table that we discussed during the presentation. Browse that file and look for timer 0 subtimer A. Be careful here. Okay? When that timer interrupt occurs, the NVIC, the nested vectored interrupt controller, will look in this vector location for the address of the ISR, the interrupt service routine. That address is where the next code fetch will happen. So you need to carefully find the appropriate vector position and replace it. It should say int default handler with the name of your interrupt handler. Now we're typing this, but I suggest you copy and paste this, since if you get a single case statement or anything wrong, it will not work. You also need to declare this function at the top of your file as external. Otherwise, the startup ccs.c will have no idea where it is. So up on the top of the code, you'll see extern void under C under int 00. Add the extern void timer 0 int handler right below it as shown below. Click the Save button. So since you've done everything right, in step 14, compile and download your application by clicking the Debug button. Now there's a couple different ways to do this. You'll notice the hammer. You can drop the hammer on your code and build all of your code first to see if there's any problems. Another thing you can do is right-click on main.c, for example, and you can say build selected file if you're wondering if that file has some sort of a problem. But since we're doing it all together, and hopefully we've done it right, we can just click on the Debug button and it will do it all at once for us. So after a successful build and a successful download, your debug tools will appear. Click the Resume button to run the program that was downloaded to the flash memory. If you've done everything right, the blue LED should be flashing on the board. Very, very nice. When you're done, click the Terminate button to return to the editing perspective. In step 15, find the line of code that enables the GPIO peripheral and comment it out as shown below. Well, now our code is going to be accessing the peripheral without the peripheral clock being enabled. This should generate an exception. In step 16, compile and download your application by clicking the Debug button on the menu bar. Now go ahead and click the Resume button to run the program. You may have noticed that the blue light is blinking. The program seems to be running just fine, right? The blue LED is flashing. The problem is that we enabled the peripheral in the earlier run of our code. We never disabled it or power cycled the part. In step 17, click the Terminate button to return to the editing perspective. So what I'm going to do is remove and reinstall the USB cable on the LaunchPad board to cycle the power. This will return the peripheral registers to their default power-up states. The code that you just downloaded is running, but note that the blue LED is not flashing. In step 18, do a compile and download of your application by clicking the debug button on the menu bar. When that's done, click the resume button to run the program. Nothing much should be happening. Click the suspend button to stop execution. You should see that execution has trapped inside the fault ISR interrupt routine. All of the exception ISRs trap in a while loop in the provided code. I'd like to point out that that probably is not the behavior you want in your production code. In step 19, remove the comment back in main.c and compile, download, and run your code again. I'd like to point out that, if I haven't already, that the perspectives in Eclipse-based tools are only views on the data. There really is no editing and debug views. They're all just views on the same data. So here you notice that we've gone back and edited in our debug window, and now we're hitting the debug button again. That's perfectly okay in the Eclipse world. So when that finishes, go ahead and click the resume button, and the blue LED should be blinking as it was before. When you're done, click the terminate button to return to the editing perspective, and go ahead and close the Lab 4 project. In step 20, here's a homework idea. Investigate the pulse width modulation capabilities of the GeneralPurpose Timer program. Program the timer to blink the LED faster than your eye can see it. That's usually above 30 Hertz. And then use the pulse width to vary the apparent intensity. Write a loop to make the intensity vary periodically.